My name is Elif, and today I'm going to tell you about the work that we've been doing over the past year constructing a database of materials properties calculated using quantum Monte Carlo methods. And so this work, I'm one part of a big team who has been working on it, Ray Plant, who's now at NIST, and Lucas Wagner, who's here in the audience today as well. To set up the problem, we are interested in bringing high accuracy methods to the simulation of properties of materials. And so when I say high accuracy methods, I guess for the sake of context, I'm an engineer who kind of has a strong foot in the physics world, and I'm interested in bringing the techniques of the physics community and kind of making them more standard in the engineering world. In this case, for instance, to understand and predict the properties of real materials. Here's an example, photovoltaic cells. This is actually not just any photovoltaic cells, they are on my roof at my house in Illinois. You know we've gotten good at photovoltaic cells if we are putting them on rooftops in the snowy Midwest, and it's worth it, and it actually is. But what's interesting is it has taken over 100 years to actually optimize the properties since we discovered the photovoltaic effect of silicon before someone like me can actually feel like it's worth it. And I was pretty committed anyway to putting solar cells on our roof. So the question is really, why did it take so long to optimize the property that we're targeting? And can we do better? Is there a way to figure out in a faster way, where do I want to put the atoms to get the desired effect? And frankly, can we put the atoms there in the first place? Maybe I know that a given composition will give me the right properties, but maybe it's not stable. So here's an example kind of looking at the material copper indium diselenide. Might seem a little bit like element alphabet soup, but what this is actually, it's a alternative competitor material to silicon for photovoltaic. So it's a thin film photovoltaic material. Because it's thin film material, it can be about 100 times thinner, lots of possibilities for cost savings that way. And what we've done here is we've actually calculated the stability of the material relative to other secondary phases that it might decompose to. And that's what's shown in these different triangles here. So it's copper indium diselenide, but maybe it's unstable with decomposition to just pure metallic copper, maybe to some indium selenide binary or things like this. And so here's the experimental phase stability diagram. The gray region is actually the part of chemical potential phase space where the material is stable. If you use kind of the conventional materials kind of computational workhorse technique, density functional theory, PBE, your triangle is kind of too small to begin with, and we do predict that the material is stable, but just barely so. And so the point that I want to make is that if the errors in the method had been just maybe a little bit worse, we may have missed the existence of this material altogether. And so that's one reason why we might want to do better than that. What else? Why else might we want to do better? Okay, so here, let's see if this plays. This is kind of a silly movie, but anyway. Other reasons why we might be interested. There are also a lot of very complicated materials out there. Superconductivity and magnetism are kind of examples of quantum effects that we run across on a day-to-day basis, but our current best quantum mechanical techniques really struggle to even sometimes qualitatively capture the right physics underlying these phenomena. And so there are a lot of reasons why, if we really want to know how to predict maybe the next best high TC superconductor, we need methods that are actually predictive from the beginning. And what else? Okay, so to set up the problem, I'm going to try to set up why Blue Waters is kind of a great platform for the techniques that we're trying to bring to these materials problems. So to get started, just kind of like a quick reminder, materials properties are largely governed by the electrons inside of the material. quantum mechanics, the governing rules are basically related to this governing equation here, the Schrodinger equation, partial differential equation that we're interested in solving. So there's a differential operator here, time derivative here, and this quantity psi is the wave function. That's the property that's the function that we're interested in solving for. The square of that wave function is the probability density. And so this is relatively simple for something like 1 electron, but it quickly becomes challenging in real materials when we have many particles, so many different electrons that interact with each other, the atomic nuclei, and other sorts of things. And so just mathematically, what we have is a mathematical problem that we're trying to solve, a partial differential equation. We want to do an eigenfunction decomposition on that. The challenge is that the function that we're solving for is very high dimensional function. If I have n electrons in my system, it's a 3n dimensional function. So it becomes very challenging very quickly. And then on top of that, because electrons are fermions, the functions that we find also have to satisfy this symmetry requirement. The wave function needs to be antisymmetric with respect to exchange. If I swap any two electron positions, the sign of the wave function has to flip. So the challenges are very high dimensional partial differential equation, and we don't really know an efficient and exact way to solve for this yet. Anytime you see a high dimensional differential equation that we need to solve for, usually you think to yourself, okay, we're going to use some kind of numerical stochastic approach to taking care of some of those multidimensional integrals that appear. We don't really have too many other options for high dimensional integrals. So Monte Carlo is the approach that we're going to use. Quantum Monte Carlo are the tools that we're going to try to bring and apply them to real materials and real systems. So here's the equation that we're interested in. Again, eigenfunction decomposition. One point that I want to make before I go on is that at most temperatures of interest, for electrons, around room temperature is relatively cold. So what that means is that the electrons in the material, for the most part, they spend most of their time in the lowest energy states. And so what we have here is we can learn a lot by actually solving for determining the ground state solution to this. So if you stare really hard at the Schrodinger equation late at night, you may notice that it kind of looks like a diffusion equation. And what I mean by that is that there's a first order time derivative on one side, and this thing here as a second order spatial derivative, a Laplacian term here. And so we can actually think about this in some sense as a diffusion equation in imaginary time, but anyway, don't worry about that. And what we can see is that, let's say that I have, what we do in quantum Monte Carlo is we set up, we use the dynamics of this diffusion equation. We start by distributing electrons in our Hilbert space. We position them throughout that 3n dimensional Hilbert space. And let's say that I'm going to show you the example for the simple harmonic oscillator. Here's what our potential looks like. I'm going to guess an initial distribution that looks like this. And if I then use the dynamics of that diffusion equation, what you see happening is I start with walkers all over the phase space. Those walkers tend to die out where the potential is high. They tend to be reborn where the potential is low. And then at the very end, we have something that looks like the wave function that we're going after for the system. So that density of walkers, I've kind of now stochastically sampled the configuration of the wave function that I'm looking for, allows me then to estimate the wave function, and then I can integrate over those samples to get any observables that I'm interested in. One thing here to be aware of, remember that I mentioned that there is this sign problem issue that we have, which is that we need to carry out a constrained optimization as we evolve our walkers to the right distribution. That's because the wave function itself has to satisfy this anti-symmetry constraint. Typically, the symmetric solution is the one that is lower in energy in the spectrum. And we need to project out the anti-symmetric solution from here. There are ways to do this, but it's very challenging in practice. The noise exponentially grows, the signal-to-noise ratio goes to 0. So how do we get around this? It's not very easy. Here's where we're going to introduce an approximation. The approximation that we're going to introduce is called the fixed node approximation. This is one approximation to many-body Schrodinger equation solutions. The idea here is that, so here's the same potential. Now my trial wave function has a node in it here. And once again, I'm going to initiate the process, and I'm going to see where things go. In the fixed node approximation, what happens here is that that node stays fixed, and my walkers distribute themselves to the best possible distribution that's consistent with those constraints that are here. So for those of you who know this, actually what we found is the first excited state of the simple harmonic oscillator. And actually, this is what we can take advantage of when we try to calculate excited state properties of materials as well. What does diffusion Monte Carlo actually give us in real material? So here's kind of why this works so well for us on blue waters. What we do at the end of the day is then we sample each one of these pictures is one possible configuration of electrons about a real material. And you'll notice they don't look like random distributions of electrons. They actually bunch up in places close to the nuclei. They avoid certain regions there. We sample over and over and over again. 6 of them here. We do this 1,000,000 times. And then we can actually obtain the energy and other observables of the material itself. So just very technically, kind of, here's the approach that we use. We start with the positions of the atoms. We need to generate a trial wave function, or a guess, to start from, and that usually comes from density functional theory. We take those cone-sham orbitals from density functional theory. We create a Slater determinant out of those. We actually take a first step, which I didn't talk a whole lot about, but we solve we optimize parameters in a wave function, in a many-body wave function basis, usually in a Slater-Jastrow form. And then we start fixed node diffusion Monte Carlo, and that allows us to improve our description of the wave function and then the material. And so here's an example. This material here is it's kind of a parent material for a superconductor. You can tell that we're doing better each step of the way because the energy is dropping. It's getting lower and lower as we go. So here's just the Slater determinant energy. When we introduce 2 or 3-body Jastrow function, it actually drops by about 50 electron volts or so. And so that's quite a large drop per formula unit for this material. And then when we go to fixed node diffusion Monte Carlo, we're able to recover about another 10 eV or so in there. Okay, everything in this box we do using the QWalk code, which I'll talk a little bit more about later. So, okay, so why does this work so well on blue waters? Well, at the end of the day, we are doing sampling, and so sampling is relatively easy to parallelize. Here's our performance, speed up in thousands versus number of cores. Pretty good, up to about 70,000 cores or so. Here's the parallel efficiency, again, plotted versus the number of cores. You see a little bit of a drop-off. I don't know if the colors here are so obvious or not, but we're trying to understand where the drop-off is actually coming from. The blue bars here and there, that's related to input-output, so I/O issues. The red bars there, that's kind of a one-time startup cost as well that's built in. Okay, but why do we think it's good? Why do we think it works so well? So here's one example, and here's what we've been able to do on blue waters. Here are our calculated band gaps versus the experimental gap for a collection of materials that we've looked at recently. If you're familiar with density functional theory, you'll know that we're looking at materials that are pretty challenging. So oxides, superconductors, correlated materials, other sorts of things. And we, without any adjustable parameters, managed to fall pretty close to the experimental value. And so this is in comparison to what comes out of conventional density functional theory as well. We can actually calculate properties that can then be measured in an experiment. So here's an example of the structure factor that's been calculated for graphene. This is, so the color turned out a little bit funny here, but this line here towards the bottom is from inelastic X-ray scattering. This triangle comes from the Slater determinant description, and then what's here, coming into much better agreement with experiment, is the quantum Monte Carlo description of that structure factor as well. Okay. All right, so like I said, our goal is to kind of take this technique, which has been used quite a bit in the physics community, and try to apply them to real materials and make it kind of more a part of the engineering materials kind of standard toolkit. It's hard. Maybe some people remember several decades ago when we were first understanding how to apply density functional theory to materials, and we didn't really have a great intuition for how it might systematically make mistakes in one direction or another. We are kind of trying to understand some similar things as far as fixed node diffusion Monte Carlo goes with respect to describing the properties of real materials. And so I'm not going to go into a whole lot of details here, but the point is that the calculations themselves, that there are a lot of parameters that need to be taken care of. What are the pseudopotentials that we use, and what's the best choice? How bad are pseudopotential localization errors? How bad is that fixed node error? Are there time step error problems, finite size effects? Many body finite size effects can be very challenging. And so the calculations can be very tedious, and systematically understanding some of these effects can be very challenging. What's nice is that thanks to Blue Waters, a lot of assessing this systematically is no longer limited by computer time, but actually is a human time issue. To be honest, I wouldn't really have ever thought about trying to apply this technique across the spectrum of materials without having such once somebody makes that level of resource available to you, it kind of opens your mind to the kinds of problems you might want to take on in a different way. So how do we go about then understanding how to optimize the simulation parameters when we're trying to take a technique and really understand for the first time what it takes to get real material properties right? So the solution that we came up with is this. We call it Quantum Monte Carlo Database. I was showing this to a friend of mine once, and she said, it looks like the letters I got when I played Scrabble the last time. But the idea here is that we developed kind of an automated workflow for the calculation of materials properties using fixed node diffusion Monte Carlo. And the workflow looks like this. We start with a crystallographic information file, CIF file, for a given material. In an automated way, we generate the standard input for a density functional theory code. In our case, that code is crystal, and we use that to generate the trial wave function that we need in quantum Monte Carlo. From there, this, by the way, is kind of a bunch of Python scripts piled together. And then from there, in an automated way, we run the DFT calculations. We take the results of those DFT calculations, the orbitals, and then what we do is, from that, we assemble our trial wave function, and then we perform the QMC simulations on Blue Waters using the QA code here. At the end of the day, then we gather all the provenance, the results, and generate a database entry, goes into a JSON file. And this gives us in our community kind of a nice way to systematically assess what it actually takes to get the calculation right. You know, what are the best practices for using the method across these different types of materials. Can be either way. So sometimes we do actually all of this on Blue Waters. It kind of depends. Is that what you asked? Yeah, okay. The issue, the database. Okay, yeah, so that's separate. So I'll talk about the database. We are working together with the National Data Service. They're helping us put together a database that's sort of a Mongo database. And so the idea is then this JSON file that we generated, that can be automatically incorporated as a database entry. So there.
In case this is what you're asking, the database entry is just, it's pop out of the
yeah.
Workflow.
Right.
It just runs on the
yeah. It takes, yeah. Right. Mm-hmm. Okay, and so my student Josh and Lucas's student Brian have been pretty instrumental in putting together this kind of automated approach. And I'll tell you about some of the things that it's already enabled us to do. First, this is kind of just for fun. This is us developing the automated framework, looking at over time, starting from about last April to this April, the commits on GitHub. And so first implementation kind of over last summer. A lot less commits during the testing phase. Somewhere around January, we had a hackathon where our students got together and did a lot of work on kind of putting everything together and making it work. Then there is this little peak here, which is right before the APS meeting, where our students realized they had to work hard to get their work done. So, but at the end of the day, we do have this automated system now, and it's available on GitHub. My students actually, what's great is that they now use it for everything, not just quantum Monte Carlo calculations. So I think they found that they figured out how to adapt it for other approaches, and it helps a lot in being systematic. It helps you avoid being lazy, and it helps you avoid errors. So, okay, so what has that allowed us to do? Here's one example. This is work from Lucas's student, Brian, looking at high TC superconductor materials. And I'm not going to really go into a whole lot of details about the particular material itself. The point that I actually want to make here is what we gained from our automated workflow. So without this workflow, the first material that Brian looked at took about 1.5 years. With it there, he was able to do the same thing in about 3 months or so. So really helped cut down on our time. What's being shown in these diagrams, I talked a little bit earlier about figuring out what it takes to actually get the calculations right. What we're showing here, for instance, is the total energy of the material as a function of, think about this as different trial wave functions and different starting guesses. And basically the idea is that since our technique is a variational technique, we can see which trial wave function gives us a best description of the actual material wave function here. What else were we able to do? So my student Josh is taking on kind of a tour de force attempt. He's been looking at now a set of about 15 different semiconductor materials, trying to calculate their formation enthalpy and their phase stability and compare it to experiments. So if you're familiar with DFT, you know that this is something that DFT really struggles with. And the reason is that, take a semiconductor, gallium nitride, for instance, we need to see how stable that is with respect to decomposition to gallium, a metal, or nitrogen molecules, nitrogen atoms. And so that requires a calculation of 3 different types of materials, a semiconductor, a metal, and a gas. And it's not really the case that DFT makes the same level of, has the same level of accuracy for all of these. We need a technique that can treat all of them kind of on an equal footing, and that's what we get out of using a kind of unbiased Monte Carlo approach to this. And so Josh actually carried out this phase stability assessment. His first problem he worked on for me, manganese oxide, so a complicated antiferromagnetic material. Took him about 1.5 years. He's now gone through a series of several semiconductors in about 2 months or so. And also, we've had some successes with band gaps. I'm showing you some of the more challenging materials that we've looked at. So manganese oxide is one of them that I mentioned previously. Zinc selenide, zinc oxide. Again, these are materials where band gaps, as we calculate them in DFT, really are kind of not quantitatively accurate, but we find that using quantum Monte Carlo approaches does help us to land our numbers quite a bit closer with no adjustable parameters to the experimental value. Okay, so outcome of this work. Good news is we're able to compute highly accurate reference data for materials now more systematically and with a lot less human time than before. It's allowing us to gain some scientific understanding of how electrons interact in materials and how that results in the properties we see. And we're putting together this first materials database of properties calculated using quantum Monte Carlo. Here's some of the related works. And finally, Thank you, NCSA, Blue Waters, and especially Josh and Brian, who've done a lot of the work for this.